In this presentation, we will be working out several examples of binomial random variables. We will be using our calculator to do the calculations. If you need help with using your calculator, look for the video entitled Using Your Calculator to Compute Binomial Random Variables. The syntax for the binomial random variable are as follows. You're going to use the second distribution key. And to calculate the probability that a particular binomial random variable equals a single value, use the binom PDF function. And the syntax is binom PDF, open parenthesis, n, comma, p, comma, number, close parenthesis, where n is the number of trials in your binomial random variable, p is the probability of success for each individual trial, and number is the number of successes that you are computing. If you are interested in a range of values, you'll use the binom CDF function. And the binom CDF function syntax is very similar to the binom PDF function, except for when the calculator computes the value, the probability will be the probability that the binomial random variable, the number of successes, is less than or equal to the number that you put in to that function. If you need extra help with using your calculator with these, please do consult the video on this website. We'll go through a number of examples. In the first example, a hunter fires at 10 turkeys with probability of success, the probability of killing a turkey, is 0.1. We want to know the probability that he bags exactly 3 of them. First, let's identify the different numbers in this problem. 10 represents n, that's the number of Bernoulli trials. Each trial is shooting at an individual turkey. P, the probability of success, is given as 0.1, and 3 is the value of x. That's the number that we're looking for. The random variable itself is defined as the number of turkeys killed out of 10. And the symbols that we'll use is p of x equals 3. And the thing I'll type into my calculator is binom PDF 10, 0.1, and 3. The probability ends up being 0.057395628. You don't need to write down all of those digits for your answers. 4 digits is sufficient. But the calculator will give you 10 digits. And you should keep around the 10 digits for any additional computations, but for your answer, you just need 4 digits. So this is a basic binomial probability problem. Let's take a look at a little bit more complicated binomial probability problem. In this problem, we're looking for the probability that more than 10 students out of a class of 12 pass a particular class. So for this problem, n is 12, p is 0.97, that's the probability given for success for this particular class, and x is 10, that's the number of students that is given in the problem. However, I'm not just interested in 10 students passing. Notice that the problem asks for the probability that more than 10 students pass. Anytime you have to compute a probability of a range of values like this, you're going to use the binom CDF function, which is a cumulative distribution function, and that will give you the probability of a range of values rather than a single value. In this case, x is the number of students who pass this class out of 12. And I'll begin this problem by computing the cumulative distribution function for x equals 10. So that's binom CDF 12, 0.97, 10. And the calculator gives me the value of that probability as 0.0486 and so on. Now remember that this is the probability of x being less than or equal to 10. That's what the binom CDF, or the cumulative distribution function, is defined as. We want to know the probability that x is greater than 10. Look back at the problem. It says, what is the probability that more than 10 students pass? More than 10 is the same as greater than 10. So I have the probability of x being less than or equal to 10. To get the probability that x is greater than 10, I'll subtract from 1. This is similar to what you do if you know that the probability of rain is 60%, then the probability of it not raining would be 40%, 100% minus 60%. We're going to do the same thing here. The probability that x is greater than 10 is 1 minus the probability that x is less than or equal to 10, and that is given after calculating is 0.9513. Here's another problem. This one is another relatively simple example of a binomial random variable. In this case, a basketball player is given 3 free throws, and we want to know the probability that she misses all 3 of them. Notice that here we're just interested in a single value, that is, that she misses all of them, rather than a range of values. And so I'm going to use the binomial PDF, or probability distribution function. Here, n is given as 3 because she is given 3 free throws. P is given as 0.6. That must be her free throw percentage. And x is, or the number that I'm interested in, is 0. We want her to miss all of them. The random variable itself is the number of free throws made out of 3. The function I'll use is the binomial PDF function on my calculator, and the arguments are 3, 0.6, and 0. And your answer should be 0.064. And that is the probability that this particular basketball player misses all 3 of her free throws. Now a slightly more complicated example again. If we play roulette 10 times and bet on black each time, what's the probability that we win 5 or more times? Notice that in this case, we're looking for the probability of a range of values. And anytime you're interested in the probability of a range of values, you use the binomial CDF, the cumulative distribution function. This problem, though, is even more complicated than the other cumulative distribution function that we did because of the wording of the problem. Let me explain. First of all, we need to know the parameters. The n is 10 because we're going to play 10 times. P is given to us as 18 over 38, 18/38. The reason for that is that there are 38 slots on an American roulette wheel, and 18 of those are black. But if you didn't know that, it's given to you there. So 18 out of 38 is the probability of winning. And the number I'm interested in is 5 or more. The random variable itself, x, is the number of wins out of 10. And it may be tempting to try to compute this value, the probability that x is less than or equal to 5, because 5 is the number given in the problem. But bear in mind that we're interested in the probability that you win 5 or more times, which would be 5, 6, 7, 8, 9, or 10. The probability that x is less than or equal to 5 is the probability that you win 0, 1, 2, 3, 4, or 5 times. And when you subtract that probability from 1, you'll have the probability that you win 6, 7, 8, 9, or 10 times, and you'll miss the 5, which is supposed to be part of your answer. So instead of computing that, I'm going to compute the probability that x is less than or equal to 4. Notice that I'm trying to do the opposite of the what the problem is asking for, and the probability that x is less than or equal to 5 is not a perfect mirror image or opposite, whereas x is less than or equal to 4 is. If you're still not convinced of that, write down the numbers from 0 to 10 and circle the numbers that we're interested in. We're interested in 5, 6, 7, 8, 9, and 10. The leftovers will be 0, 1, 2, 3, and 4, which is exactly what I'm going to get when I compute the probability that x is less than or equal to 4. Once you realize that, the rest of the calculations are easy enough. I'll type binom CDF 10, 18/38, 4 into my calculator. And the number I get is 0.4431, and so on. Subtract that number from 1 to get the probability that x is greater than 4, which would be 5 or more. And that probability ends up being 0.5568. For the final problem, I want to share with you a problem that you could do one of two different ways. Let's take a look at this. A couple plans to have 4 children. What's the probability that they are not all the same gender? Now, when you first look at this, you might not see what numbers we're interested in. So let's see if we can summarize things. First off, the number of trials are the number of children that this couple is going to have. So n is equal to 4. The probability of success, well, you can define success however you want, whether it be having a boy or a girl. It doesn't matter. The probability of each of those genders is 0.5 or 1/2. There's a 1/2 chance for each child to be a boy and a 1/2 chance for that child to be a girl. Finally, to figure out the number or numbers that we're interested in, take a look at the statement, the question. It says, what is the probability that they are not all the same gender? If you have 4 children, having all of the same gender would be having all boys, or 0 girls, or all girls, which would be 0 boys. In either case, whether success is defined as having a girl or having a boy, the things that you don't want are to have x equal to 0 or x equal to 4. Here's where the choice comes in. You can either compute this as a range of values, that is, I'm interested in having between 1 and 3 girls, or you can compute individual values and then subtract from 100% or 1. I've chosen to do the latter in this presentation, but you could just as soon do the former and get the same answer. To do the latter, what we'll do is we'll first compute the probability of having 0 girls. So I'm defining success as having a girl. And the probability of no girls is the binom PDF 4, 1/2, 0, which is 0.0625. Then I compute the probability of having 4 girls, all girls. That's binom PDF 4, 1/2, 4. Finally, I subtract these two values from 100% to get my final answer, which would represent the probability of having 1, 2, or 3 girls. And that probability is 0.875.